Okay, so now we're going to show you how one data integrates with CDMI and REST protocols. So first of all, I need to log back to one zone. All right. I will go to the Sci-GaIA provider, create a dedicated space, and I will call it CDMI space. Right. Now I need to create some support. The procedure is the same as I showed previously. Right, we are ready to go. And now, I've prepared some scripts to show you how we use CDMI protocol. Here is an example file which I will upload using this script. It basically makes a request to the endpoint, which is defined as Catania provider in CDMI space, and it will the file will be stored as a file.txt. But before I do that, I need to fetch a token. So I click here. Create client token, copy that. Okay. And now I will upload the file. We've got a positive result. Now we can verify it in GUI. And the file is over here. Now we will download the file using the script. It basically, again, makes a GET request on the path. CDMI space / file text. So go ahead and do that. And we got here the content of the file. Next, I will show how to set some. Yes, question.
Just a small question. The token has time validity, or if I create a machine with some scripts running in the ground, I have to change the token as a regular interval.
Currently, the client token has a long validity, and the client itself passes the token on with shorter validity and refreshes it.
So it's the client who creates a new token from this token I'm doing that.
Because the tokens are based on macarons, they can be further constrained. So we can create a token that we say that it's valid until now plus 20 years, for example. And then we can add another constraint that says valid now plus 1 hour.
Okay, but how it works right now? I mean, if I create a machine that performs operation in the ground, I have to change the token can be used for a long time, or I have to change the token every couple of hours?
For a long time.
Oh, that's good. With the current installation, okay.
So now we will write some metadata, some extended attributes to the file. It's again a request with some CDMI specific headers. Let's go ahead and do that. Right, again, we got a positive result, and we can fetch the extended attribute using a different request, which simply asks for got them. And finally, I will delete the file using the request. This again, it's very simple, very intuitive. And it says it is deleted. And when we refresh GUI, we see that the file is done.
Metadata user, the user can add to the file. They are not metadata, I don't know, the attribute of file
There are extended attributes.
Okay, extended attribute. Okay. You can write on the interface or in the command line. I mean, this is an extended attribute. You can add with the CDMI, and you can add also on the web interface.
Currently, there is no support in web interface.
Okay, only but with the CDMI, yes.
CDMI and also via REST, and I will show
Okay,
you.
okay. No, because you get the value, but community when you write the value.
Yeah.
Okay.
I had another question. I may have missed this, but before we did the interaction with the providers via Fuse, now we're doing it via CDMI.
Yes.
Where is the disambiguation? Like how do the providers know that they use the CDMI protocol now, whereas before they were using Fuse?
Actually, now Fuse clients connects to a different port. It's port 5555.
And that's in the environment script that you sourced in the beginning?
Yes.
Okay.
Yes. Yes. And now I'm making requests on port 8433.
Okay.
Or 844.
There is an effort right now to centralize the ports to 43.
We would like to minimize the amount
we
of
need
ports.
this for DNS and 443 with a proxy. With
Some prefix so that we can
Yes,
distinguish.
it's just different endpoint,
Yes.
different point.
Oh, that's harder for provider because it's not HTTP based provided to client. It's not HTTP based.
Okay,
So
okay, yes. Because there is TCP stream, raw protocol. Okay.
So there would have to be a more involved routing logic with logic afterwards.
Yeah, I was just wondering if there was like an application in front of the provider that's
Not right now.
routed the switching.
So that's all because for CDM. Yes.
Is it possible to save 3D or 4D images on the platform?
Once again, I haven't heard you.
I said, is it possible to save 3D images?
3D images, yes.
Yes, 3D or 4D or images.
We are storing binary data, so we
Only binary.
So we don't care
What kind of images?
It can be anything. It's
Okay.
just a piece of light. So it can be anything. Right. Now we finished the part about CDMI, and we'll move on to the last part where I will show our REST API. So to do that, I will create a last one space, which I will call the REST space.
You support all the API of CDMI, all the specification of the CDMI, or is it subset?
No, we implement a part of specification. I think we have a documentation that.
Okay, there's on the one data, there's the list of API you support.
It's a subset.
Okay. I mean, there's a document with all the API you support in the one data site.
I believe so. Yes.
Okay. But the basic operation you support. I mean, just upload, download, and some
The
metadata
things
management.
we think are the most important are there.
Okay.
Okay, and now I created the space, and I'm supporting it in both providers, because I will show you in a while the endpoint for a replication file. So we need a support in both providers.
With REST API, you have all the options for one data. REST API is for everything. Right now, or you have also, I mean, all the future of one data is supported by REST API, or with some
We are trying to make all the operation available in REST, but it's hard to say whether there are.
REST is a new addition to one provider. It's
For
not-
sure, you can upload, download files via REST,
Okay.
modify extended attributes, and so on. You can support spaces and create spaces and so forth.
But the CDMI is absolutely we have something. the web interface, you miss something that you can do with REST API. If you get, but REST API still there is something you cannot do with REST API, but with other. So no, there is no one method to have all the future of one data. That mix if you want everything.
Yes, I
At the
guess.
moment, yes.
Okay.
We will try to
The
unify.
features are scattered.
Okay.
And here and here. So now. Alright, so but another bunch of scripts in REST directory. First of all, we will make a long call request to a REST space I've created just a few seconds ago, and we will see the changes that happens in this space. So while we upload, for instance, a file to the space, we will get a feed from this request, which will say what happened in this space. So before I do that, I need to just ensure I've got a right token here. We are making a long call request to a space, but we need to provide a space ID. To get that, you can easily go to the administrative panel and copy.
You have to provide ID. The name is not enough. You have to provide ID.
No, you have
Because
to
the name is not unique.
Inside the
Inside
the
one
provider.
Inside the provider as
It's
well.
not unique. Okay.
You can name your space whatever you like.
Yes, but I was thinking it was not unique inside the workspace, but it's also inside with the provider.
In the zone.
In the zone, yes. In the
the
zone.
space was also in the zone, and it's not unique in the zone.
Okay.
So now I've made a request and it hangs and waits until I do something in this space. So let's go ahead and do that. Let's upload a file. Okay, and here we've got a bunch of changes which, for instance, concern the modification time of the space folder, the information about the uploaded file, for instance here, and so on. We can go ahead and change the mode of the file. And we should also get some changes over here. So the file changed in a space, and we get a constant feed of changes right here. And also we can delete this file. And after a while, we should get info where the deleted field will be set to true. We have to wait a moment due to caches and timeouts.
You can monitor only the space or also a single directory or whatever. You can specify what you want to
And
monitor.
currently, we support only
the space, okay.
spaces. Oh.
Okay.
And here we have that the file named Sicily05 has been deleted. Okay, so it's about the changes feed, and now we will write some extended attributes to the file which I will upload right now. Let's upload another file. Okay. We can get the attributes of the file, and it requires me a file path. So let's equals png. Great. Rest. all 6. Yes. So the current, it's not an extended attribute, it's just a normal attribute. We currently just support the mode of the file, but if we provide a flag, which is simply added here as a query string, we get an empty list. We can go ahead and change the mode of the file. 777. Okay, we need to 6G 777. What it does, it makes a request to this file with a mode set to 777 in the body of the request. And now when we get the attribute of the file, we see that it's now 777. Now let's add some extended attributes. And we again provide img, and we name it out1. Okay. And add another one. Now when we get we get a list of attributes. We can also fetch a specific attribute. And we get only the selected attribute. What it does, it made a request. Here we specified that we want an extended attribute, and it should be the name attribute. We can also override the attribute simply by making another request for the same attribute with a different value. And now when we get the attribute, we see that it's the value has changed. Right. So now we can also get the via REST, we can get the same blocks distribution which we saw in Web GUI. We can get replication, and I guess yes. We got a result where we have a provider ID with blocks, which is an empty list. This is ENFN provider, and the other provider, which is Catania provider, who has the whole file. Now we will go ahead and replicate the file from Catania provider to ENF provider via REST call. So we replicate file. And here we have to provide file path. And also ID of a provider which we want to replicate this file. This makes a request to Catania provider with an ID of an ENFN provider.
Okay.
So to get the ID of ENFN provider, we can navigate to the administrative panel of ENFN, and here we have provider ID. We basically and we got in return and transfer ID. With this ID, we can query what is the status of the transfer, whether it has completed, whether it has failed, and so on. So we can get to transfer and provide this ID. And it says that it is completed. We can verify that by making again the request to get the replication of this file. And now we see that the file blocks are in both providers. And the same is, of course, here in. Okay. I guess that's all I've prepared for REST API. Are there any questions?
What did I think?
Yes, because we have a few more slides just to conclude. So thank you very much for your attention, and
These sample bash scripts are available somewhere?
it will be.
Be available.
Yes, yes.
When you do a post, what kind of content up you might send the JSON block with all the stuff you want to post?
Yes, for instance, when I set the mode of the file,
Yes.
I've sent a post request with a body where the body was a JSON with a one field mode and the value. And actually now we only support JSON format for the request.
For the the output is also JSON format, of course, because the output from the query is JSON.
Yes, yes, the output is always JSON.
And there's no RTOS support. There's no RTOS support.
No, no.
No, I
It
mean,
supports only JSON.
no, it's JSON is okay. There's
Okay.
no support for links. No, REST API. You have the links inside the hyperlinks to the resource and so on. There's a lot of the.
I guess we don't support it.
There's okay.
Although but we can in the future.
Everything is possible.
Yes, everything.
With time, people working on
So-
something, you can do a lot of stuff with that. Okay.
Thank you.
So I guess the camera can go back there.
You finished with Jensen?
No.
The rest will be slides.
Okay,
Just a few.
okay, perfect.
And possibly, if we have the time, which I guess we do not, we may have hands-on.
Well, I mean, what you could do, you could just show how to show to them how they can exercise themselves,
Okay.
and if they can follow up even later.
Okay.
Yes.
So, the last few summer slides are, first of all, the one data with the HBP, which stands for Human Brain Project. The Human Brain Project prepared a service that was based on one data as well as Dcache to compare the services. And in this project, they set up their Atlas Viewer application, which is an HTML with JavaScript that shows brain sections. The Atlas Viewer fetch data from the Image Viewer application. Image Viewer is a service that reads data from storage and exposes it on a REST interface. So Atlas Viewer fetches data through request to a REST interface provided by Image Viewer. So the Image Viewer had one client mounted inside of the container, and the one client interface with one provider and fetch data from the HBP scans space, which had 5 terabytes of support. The file with the brain scans had about 5 terabytes of size. We also set up an Nginx server to load balance the REST request from the Atlas Viewer to the Image Viewer. So we actually had the 5 Image Viewer containers that were serving data through REST to the Atlas Viewer, which was making a big amount of requests because for every part of the image was rendered with a separate request for data. And we measured the performance of this setup with 5 Image Viewer containers with one client mounted. The one client was mounted over a parallel file system, which the name of which I don't recall, but it was very performant. And this is the result of the measurement. At the peak point, the 5 containers reached 56 gigabits of, almost 57 gigabits of throughput. this is possible because one client has a feature where it can directly connect to the storage. It can auto-detect that the storage used by one provider is available on the current machine and talk with the storage directly instead of proxying the request through one provider. And then we get results like this, which are, it's a relatively common use case in clouds that we can have the storage mounted on our client machines as well. And in this case, one data is used for metadata management and providing a structure and other features such as REST and other things. And for the plans for the near future, we are integrating with Open Data Platform. The basic use case that we envision for One Data would be that you would create your space, put your data that you want to publish there, then create a snapshot. So you take your space with files and you create a snapshot. You can then modify your space and create another snapshot. And only differences between the snapshots will be stored. Then the collection can be published with a DOI by a service that assigns DOIs and put in public services for data discovery, like, for example, dataset. A user can discover the data through DOIs and access them under permanent link. The user can also mount the data that he was given open access to with the use of one client.
By using the DOI. So they would resolve the DOI.
Yes. I mean, this is not implemented yet. This
Yeah.
This is just a concept.
is not just a concept, it's in progress concept.
Okay.
It's a good concept.
Concept in progress of implementation.
Right.
And the user can also fork the DOI and the data under the DOI. And the data will then be lazily replicated, which means a mixture of copy on write and scheduling replication for a later date.
How do you maintain the connection between the forked data and the original data? How do you deal with the provenance? Well, how are you going to deal with the provenance? Have you thought about that?
We don't yet.
Yeah, okay.
We are thinking about it.
So, I mean, I'm asking because I also have to think about this for a particular project. So, yeah, if you have ideas.
Not yet. We have people dedicated to integrating with open data, and they are charged with designing the solution for this particular problem. And that's it for the plans for the near future, except all the features that we discussed previously. Now is the time for a hands-on demo because we are skipping the hands-on demo. Here is the URL to our HIP chat room with guest access enabled, where you can, when you log in onto the one zone that is set up for Indigo, which the link of which we will provide in a moment, you can then send us support requests in this room, and we will support your spaces, so you can play with one data, maybe invite each other into groups through the HIP chat room and see how it works for yourself.
The URL of the one zone is onedata.indigo-datacloud.eu.
I will put it on the display in a moment. So yes, summarizing, we have one data provides access to distributed multi-provider storage, multi-provider, multi-data center, and multi-federation storage for a user. It has flexible access control lists. You can share data between federations. We have the POSIX client. We have various other interfaces available right now, and with more features coming, of course. And interfaces in the works like WebDAV and FTP. It is scalable, and as we've seen, in the HPP demo, it can be, one client can be deployed in use cases where you can enjoy the benefits of one data grid with very little overhead on the file system below. We have support for open data scenarios in progress, and we are currently developing one data under Sci-GaIA, Sci-GaIA Engage, and Indigo Data Cloud. And that will conclude the presentation. Let me just put the link to our one zone on the screen. If I get my mouse back.
To set up a one zone for test is complex, or to set up a one zone with one provider and so on
Well,
is a complex procedure, or it's
No,
easy
it's
to
not
do
complex.
for
You can set it up on your laptop in about 3 minutes. The same environment.
everything? One
Yes.
zone plus one or two providers in one laptop.
Yes,
It's possible.
yes, I can see that.
Okay.
There I show you how.
Just. But if you want to show it,
So here's the link for the one zone where you can log in, create your spaces, give us your space support token, we will support your space, and you can hack on. So thank you, that's all the class.
Thank you very much to you. So we can keep this for the next day, so to let people playing with it?
Yes.
Okay, that's great. So copy the link. If you want to exercise yourself with one data, that's the link to use as an entry point. Okay. Questions?
Yeah.
Before we move to the next tool. I think we had a lot of questions already.
Yeah.
So, okay, so we can move to the next tool that is Ophelia. So we are moving from data management to open data to data analytics. Alessandro Danca from CNCC will present Ophelia and its functionalities. You should wear your microphone, okay? Okay. Laser pointer, yes. Let's see if it works. I don't know if I have enough battery here, but I can. No, it's out of battery, this one. Ah, no, that's okay. What do you do? Se stai seduto o stai in piedi su questa parte qua, così possiamo vedere. Perfetto, allora questo bottone centrale, Ok. What do you want?
So, good afternoon everybody. My name is Alessandro Blanca. I belong to CNCC. We run a center on climate change foundation. In particular, I belong to the Advanced Scientific Computing Division. My presentation, I show detailed information about the Ophelia, our big data analytics framework for climate change we developed in our division at CNCC. The outline of my presentation, first of all I will show you the analytic requirements and big data challenges in the climate context. Then I show you information about the Ophelia, in particular concerning the architecture 1.0 with the definition of the new storage model we implemented to support the Ophelia processing with primitives and data and metadata operators. Then I moved to the architecture version 2.0, focusing the attention on the workflow support with some real use cases. Then I give you some useful link and documentation, website, GitHub, YouTube, IP, and so on. So when we start the design of the Ophidia framework, we collected many data analytics requirements and use case from our scientists, our web scientists, and CMCC. So requirements we collected and needs focus on particular on time series analysis, data subsetting, model intercomparison, multi-model needs, massive data reduction, and so on. Also, other kind of requirements, non-functional requirements, as performance, usability, and extensibility. In addition, volume, variety, velocity are key challenges for big data in general, and for climate change science in particular. So the goal is to move from the current workflow to a kind of beta exascale workflow. So at the moment, the flow of operation performed by each scientist is more or less this. So first of all, there is a search and discovery phase. Then there is a heavy data download from the source to the desktop-based, to the desktop of the user or the target machine. Then there is the computation, desktop-based data analysis. Now we want to move to another approach, to another paradigm, moving the computation server side in order to allow a lightweight data download. So the Ophidia project is, as I said before, a CNCC Foundation research project addressing big data challenges for e-science. Provides support for declarative parallel server-side data analysis, exploiting parallel computing techniques and database approaches. It exploits a multidimensional data model, providing the generative abstraction for access and analysis of scientific and dimensional data. In a nutshell, Ophidia provide a big data stack for scientific data analysis. Its features regards time series analysis, but in general, array-based analysis. Data subsetting by values or by indexes, data aggregation, model intercomparison, all-up procedures, and so on. It uses parallel operators and parallel I/O. It supports complex workflows and operational chains. I will give you an example of this, the second part of my presentation. It is extensible, using simple APIs to support framework extensions like new operators and array-based primitives. We develop at the moment more than 50 operators and more than 100 primitives to support the user requirements. It provides multiple interfaces. You can say this interface is the SciGOMS or GCWS. Programmatic access via C APIs or Python APIs. It supports both batch and interactive data analysis. This slide shows the Ophidia architecture from an end-user perspective. So in order to hide the complexity of the entire stack of the Ophidia framework, we developed the terminal, the Ophidia terminal, that is a commands interpreter with no GUI, like bash, serving as a client for the Ophidia framework. So the Ophidia framework is server-side processing, and through the OPH term, we send commands to the framework. So this slide shows the Ophelia architecture. Basically, it is formed by 4 layers. The first one is the front end, is the Ophelia server. It provides the declarative language and standard interfaces. The first layer is the compute layer. It is formed by a pool of compute nodes, and it implements the analytic framework. Third layer is the I/O layer, formed by a pool of I/O nodes, and this layer is applied on the array-based primitives using MySQL instances and user-defined function like it. The lower layer is the storage layer. We specifically implement a new storage model based on partitioning and on hierarchical data mapping. So, I start the discussion, the presentation, speaking about the new storage model we implement and the partition and hierarchical data management. So, the Ophelia storage model is a two-step based evolution of the star schema to support scientific data management. It relies on implicit and explicit dimension for specific representation of data. The implicit dimension identifies the arrays. The explicit dimension identifies the tuples, the rows inside our tables. So the first step includes the support for array-based data, and the second step includes a key mapping related to a set of foreign keys. It is important to say that the second step makes the Ophelia storage model and implementation independent of the number of the dimensions. So this slide shows the implementation of the storage model of Ophelia. This is the representation of the data fact model. So we have a measure and the related dimension. The classic rollup implementation foresees that we have a table with one column for each foreign key related to the dimension we want to consider. In the last column, we have the measure, the scalar value we want to store. Think about, for example, a dimension as latitude, longitude, altitude, and time. So, in the fourth column, we have, for example, the temperature. One temperature for each point of the world in a specific time step. The first step is the representation supporting n-dimensional arrays. So we collapse one of these dimensions inside the measure column. This way, we have an array of measure. For example, an array of temperature. One value for each time step. The second step is a key-based role implementation supporting n-dimensional arrays. So, we map the remaining foreign keys related to, for example, latitude, longitude, and altitude to a single key identifier. This is our final bit table, formed by two columns. First one is related to the three-dimension value step. The second column is an array of values. For example, one value for each time step. This is our final representation of the data. This big table is then distributed across a pool of I/O nodes. Each I/O node contains a pool of I/O server, for example, a set of my single DNS. Each DNS manages a pool of databases. Inside each database, we have a certain number of fragments. Each fragment contains a subset of this bit table. So, moving to this third layer, I'll talk you about the array-based primitives and development using the user-defined function plugin. So, Ophelia provides a wide set of array-based primitives to perform data summarization, subsetting, predicates evaluation, statistical analysis, compression, and so on. It's important to say that primitives come as plugins and are applied on a single data group chunk, so a single fragment. So if a user wants to develop his primitive, it's very simple because it's enough to develop the code of the primitives and then insert this primitive inside the system as a plugin without the need to recompile all the code. Primitives can be nested to get more complex functionalities, and the compression is also a primitive. So as I said before, new primitives can be easily integrated as additional plugins. This is an example of one developed primitive, the OPH mapped primitive. So starting from this input data, so you can see the array, one line, one row for each array. We can apply the OPH mapped primitive in order to find, for example, the sign for each value contained in the array. So this is the statement, OPH map measure is this column. OPH sign, the function we want to perform, and the type. This is the input. The output is always in an array-based form. In each array we have all the sign of the input data. This shows the same example in terms of graphs. So this is the input, and so here are the output, one for each array. Concerning the OPH map primitive, we developed many macros, many functions, and this is the list of the function we developed. The sign is one of these. And this is the way you can use to launch the OPH map primitive. Measure macro. So for example, OPH map sign and the type. Other example of primitive, the OPH box plot. So we want to find the so-called 5 numbers, the minimum, the maximum, the first quartile, the third quartile, and the average starting from an array. So we can use OPH box plot measure with the type. This is the input and the related output with our 5 numbers. The same way, in graph manner, this is the input table and this is the output. As I said before, primitives can be nested together in order to compose much more complex functionality. So, in this case, we want to extract the box plot of a subset of this input data, and these input data are compressed. So we can use simply a single statement with other functionalities nested together. of pH uncompressed to uncompressed data, subarray to select only a portion of the input data, and then on this input data we can apply the box plot feature in order to obtain this output. So this is the input data, this is the subset, and this is the box plot related to the subset we want to analyze. So we can analyze not only arrays but also columns using vertical aggregation. So, for example, these primitives, your pH aggregate, are able to compute some operation, for example, the average, on each column of the arrays. So, starting from this fragment, using the pH aggregate, we have a vertical aggregation and in output a single array containing the average of each element of the array. So this is the input, and this is the single array in output. Moving to the second layer, it regards the compute nodes layer and the pool of compute node in which we install which we implemented the analytics framework and the API-based section of Ophelia. So we developed more or less 50 operators in order to perform different kind of operation concerning data processing, for example, to duplicate a cube, to subset a cube starting from indexes or some values, to have an intercomparison between two cubes, to reduce some cubes into another. For example, if we want to aggregate value from days to months, or from months to year, and so on. Other operators concern the import or export feature in order to import in our storage model different kind of sources, and vice versa to export to different kind of sources data stored in our storage model. At the moment we implement the import and export NetCDF, that is the standard format used in the climate change context. Concerning the data access, we implemented many functionality to, for example, inspect the fragment so to see the values inside your cube. And also metadata management. So if you want to know the number of elements of your cube, the size of your cube, the list of the cubes you have in your environment, and so on. Concerning the operators, as I said before, we developed much more than 50 operators. This is an example. We want to reduce the arrays finding in order to find the maximum values. So we can apply the operator reduce in order to find the maximum value for each array. At the same time, we can apply an aggregate in order to find the maximum value for each column of the arrays. Important to say that with respect to the primitives, an operator works on the entire cube, so on the entire set of fragments. So the primitives work at fragment level on a single fragment. The operator works on the entire cube as a complete set of fragments. For example, if we want to split a big fragment in some smaller fragment, we can use the split command to create, for example, 10 fragments starting from a big fragment. Vice versa, we can merge 10 fragments into a single one. Another kind of operator is the subset. For example, if we want to filter to select only the first two arrays, we can use subset with some filters in order to select only two arrays, only two rows. Now, I want to show you a massive data reduction workflow, which regards the combination of 4 operators in chain in order to find the 0D apex cuboid, so the maximum of the entire cube. So, on the left you can see our cube is formed by 64 fragments. Each fragment has 10 to 4 tuples, and each tuple is formed by 10 to the 5th elements. So in total we have 64 by 10 to the 4th by 10 to the 5th elements. The first operation, in order to find the single values which represent the maximum value of the entire cube, is the reduction. We reduce all the arrays, finding the maximum value for each array. Then we aggregate, finding the maximum value for each column. Then we have 64 fragments. We merge all the fragments in a single one fragment. Then the last operation of aggregation in order to find the maximum value of the entire data set. Starting from 512 gigabytes of data, with 4 steps, we reach 8 bytes of data. That is the maximum value. As I said before, we implemented also many metadata operators. This is an example of the cube schema operator. So we can use cube schema with the persistent identifier of the cube in order to show metadata information about our cube. For example, the persistent identifier, the creation date, the measure inside the cube. In this case, is the temperature over surface, the type of the measure, and so on. This cube we have 170 fragments. In particular, this is the source file. Additional information related with the cube, a description. This information regards the fragmentation, the partitioning we use to store the data inside our storage model. So this data cube is stored on a single host, on a single MySQL for host, on a single database for MySQL. Inside this single database we have 170 fragments. Each fragment is formed by 180 tuples. Each tuple contains 24 values. So our array is formed by 24 values. This is the size. It is a small cube, 3 megabytes. This is the number of elements. And this is dimension information, latitude, longitude, and time, with the size, the relative size. Another example is the cube.io. So these operators show you the provenance of the cube. So in this table, you can see the input cube we use to perform our operation, and the output. We can visualize also this by using an image. So you can see in this case the source cubes are these two cubes. Then using an intercube we have a single cube, and then reducing, merging, aggregate are other kind of operation in order to reach our final cube. Another example of metadata operator is the export cube, which allows the user to see which data are stored inside our cube. So basically the variables, the measured variables. So we can use export cube with the name of the cube, the persistent identifier. If we want to subset the visualization on using particular filters, in this case we want to subset from 39 to 42 degrees of latitude and from 15 to 19 degrees of longitude. And for 1 to 2075 concerning the time. This is the output. So you can see latitude and longitude are in the ranges we define. And this is the array of temperature in Kelvin. One value for each time step. Another example of provenance management. This is a more complicated example. As you can see, we have many branches starting from a single input cube. We have many branches, many in operation to reach a set of output. So, as I said at the beginning of my presentation, the architecture version 2.30 moved to develop a new feature concerning, for example, concerning specifically the support for the workflow management. So we developed another module integrated into the server in order to manage workflow, to manage the dependencies between the tasks, to allow the user to use complex operation as loop, definition of variables, and so on. We develop also data analytics workflow modeling language that is extensible and extensible schema jointly defined with application domain scientists. And these are an example of some stencil we can use to model our workflow. From a system perspective, a user can define his own workflow using a JSON file like this, in which a user has to define all the tasks he wants to perform, defining also the dependencies from between the different tasks. So this is a visual representation of the same workflow moving forward. This workflow, in particular, is created to compute the maximum of the minimum temperature executed task. The orange circle represents the running task, while the gray circles represent the pending task. As you can see here, a double parallel approach